Hi, class. I'd like to wrap up some of the stuff that we've talked about in terms of probability here, section 4.3, 4.4, and then also talk a little bit about some of the stuff that's in 4.5. Attached to this, the email that you got, you should have found a sheet that looks like this. It's about a 3-page document. On this front page, we've got basically all of the rules that we've been talking about, and I want to fill in all the details on here. Some of the stuff we've done, but this is going to be kind of a nice place to go back and look at, going back and just reviewing some of the things that we learned. So first of all, for any event, the probability that A is going to occur, we said the other day in class, was going to be somewhere between 0 and 1, or between 0 and 100%. Sample space is every possible outcome. The probability you're going to get something from the sample space is going to be 100%. For any event A, this is the complement rule. Now, your book uses the other notation, which is probability of A bar, and this is just 1 minus the probability that A does occur. Right, so the complement is the probability that A does not occur is going to be 1 minus the probability that it does occur. And if you think about it over here, this is the probability of A plus the probability of A bar. These have to be 100%. Either A is going to occur or it doesn't. And if you just rearrange this using some algebra, you can come up with this equation over here. Okay, and then we talked about the addition rule. On this sheet, you can think of this symbol is the union symbol. You can think of this as just being the word or. All right, so if A and B are disjoint, mutually exclusive events, and then kind of in general what happens. All right, we've talked about both of these cases, and so the first one is if they are disjoint, that means that they can't both happen at the same time. So the probability that either A or B occurs is going to be the probability of A plus the probability of B. And then we said the other day that if they're not necessarily disjoint, this is going to be the probability that A does occur plus the probability that B does occur. And then the probability that both things have occurred are going to be included in both of these, so we end up subtracting the probability of A and B occurring. All right, so those are rules that we talked about in section 4.3. Well, I guess it's 4.2, 4.3, and a little bit of 4.4. In section 4.5, we're going to talk about some more of this stuff down here at the bottom. And I think that we hit on this idea of what happens if you have two events that are not necessarily independent. We're going to talk about this idea of independence a couple times here. What if they're not independent? If they're just two events, not necessarily independent of each other, and this is the word again. This would be and the probability that A and B occur. So if you think about the problem that we did the other day, I said, imagine that we've got a deck of cards, and I want to know what's the probability that we're going to select two red cards without replacing them. Okay, those two events are not independent because if we don't replace the card, the probability that second card is red is going to be dependent upon what happened on the first card. So if A and B are any two events, you can think about something like the probability of getting two red cards is going to be, first card, there's 26 red cards out of 52 total. And then if you pull out a red card, you're going to end up with 25 red cards left out of 51 cards that are left. Right? If you think about what these represent in terms of probabilities, the probability of 26 out of 52, that's like, what's the probability of getting a red card? Right? And then if you think about what this probability is, that's the probability that we're going to get a second red card. We'll call that event B. And that's 25 out of 51 because A has already occurred, and we're going to write this as the probability of B given that A has already occurred. All right, so the probability of two things happening is going to be the probability the first thing happens times the probability that the second thing happens given that the first has already occurred. Okay, so if we take these probabilities and just kind of rearrange them using some algebra, I'm just going to take both sides of this equation and divide by the probability of A. So the probability of B given A is going to be equal to the probability of A and B divided by the probability of A. Okay? And then there's another formula that's very similar to this. We could say the probability of A and B is going to be equal to, we could write this as the probability of B times the probability of A given that B has already occurred. All right, so all we're doing is we're just changing the roles of A and B. And if we solve this equation for the probability of A given B, we're going to end up with the probability of A and B divided by the probability that B has already occurred. Okay, so if you look at these formulas, the numerators are going to be the same. It's the probability of A and B occurring, but then the denominators are going to be a little bit different. It's the probability that the given part has already happened. Okay, in some problems it's going to be nice to lean on these formulas, and sometimes it's going to be better for us just to look in a table and just kind of count how often do these things happen. Okay, so with all that in mind then, I'd like to go to some of the problems that are in the book. Some of these problems were assigned for homework, and I just want to make sure that everybody's on the right page with these. Also, if you take a look at the other stuff that is in the packet that I gave you, what I would like you to do is, without watching this video ahead of time, I'd like you to take a stab at these questions. Okay, they're not really trivial types of questions, but what I want you to do is think about how you might answer these questions with the knowledge that we have about probability so far. Okay, some of these I think we're going to end up hitting and understanding some of the techniques for finding these probabilities, but I want you to give that a shot before you see me work through the problems as well. Okay, so let's take a look at some of the problems that are in section 4.3. In section 4.3, I want to first of all go through some of these questions about disjoint events. Okay, this is something we talked about last week. All right, and I just want to kind of talk through some of the answers here. So question number 7 was an assigned problem. And the question here is, determine whether or not these are disjoint for a single trial. In other words, if they're disjoint, that means that they are separate or not overlapping. All right, so suppose that you randomly select some person, and you said randomly selecting a survey respondent and getting someone who believes in UFOs. And then the second one is randomly selecting a survey respondent and getting someone who believes in the devil. All right, so are those events disjoint or are they not disjoint? Well, if they're disjoint, that means that there's none of the people that believe in UFOs also believe in the devil. All right, I think we can probably find some people that believe in both. So these two events are not disjoint. Okay, take a look at the next question. Not the next question, but another question here is number 11. Number 11 has to do with the drug testing again. So randomly selecting a drug screening result and getting one that is a false positive. All right, remember what a false positive is. A false positive is the person is not using drugs, but the test says that they are. Okay, and then B is randomly selecting a drug screening result and getting one from someone who does not use drugs. Okay, so are these disjoint or not? Okay, randomly selecting a drug screening result that gets a false positive. This means these people are not using drugs, but the test says that they are. And then can you also get randomly selecting a drug screening result and getting one from somebody who does not use drugs? Right? These people that don't use drugs are going to be in this set. So these are not disjoint. There are some people that are going to get a false positive, and there are some people that are also not using drugs. Okay, if we skip down to number 13. Number 13 is find the indicated complements. All right, remember the complement is the probability that something did not occur. So the Marist Poll survey showed that 47% of the respondents chose whatever as the most annoying phrase used in conversation. What is the probability of randomly selecting a person, someone choosing something different than whatever, as the most annoying phrase in conversation? All right, so if 47% said that this is the most annoying phrase, then the probability we're going to get somebody who doesn't say that is going to be the complement of that, which is just 53%, 1 minus 47%. All right, so that one, again, I think that one's fairly straightforward. Okay, let's go on to the next page. We've got a couple of problems here that deal with the drug screening again. All right, so let's take a look at number 18. All right, number 18 says, use the drug screening data in table 4.1, right, and this goes back to page 150. All right, on the top of 150, we've got drug testing results. Okay, so again, over here, this is subject uses drugs, test positive. These are true positives, false negatives, false positives, and true negatives. All right, so the question that we have is, if one of the test subjects is randomly selected, find the probability that the subject had a positive test result or does not use drugs. Okay, so a positive test result or does not use drugs. Okay, so if we look at this person, these 44 people, did they have a positive test result or don't use drugs? And the answer to that is yes, they tested positive. These people over here, did they test positive or not a drug user? Okay, the answer to that one is no, these people are not in that group. These are the ones that are using drugs that test negative. Okay, down here, do these people use drugs or test positive or do not use drugs? Yeah, they're both. And these people over here, these 860 people, did these people test positive or not use drugs? And the answer to that is yeah, these people are not using drugs. So when we think about this probability, we're going to end up taking all of the people that are in these three cells, right, which happens to be 994, and that's out of 1,000 people in the group. So 994 out of 1,000 is 94.4%. Okay, so that's the answer to this question. Now, you could have also used the rule that we have for find the probability that a subject had a positive test. Okay, so we could look at the test is positive plus the probability they don't use drugs, and then subtract the overlap. These are the ones that test positive that are not using drugs, and subtract that out. Okay, so that's another way we could do this. It's easiest just to find the three groups that are in that category and just add them up and divide by the total number, which was 1,000. Okay, another one. If one of the subjects is randomly selected, find the probability that this subject had a negative test or does not use drugs. Okay, so had a negative test, that's these two groups over here, or does not use drugs is these 90, so it would be everybody except for these 44, so that's going to give me 956 out of 1,000, or 95.6%. Okay, all right, so that's using the table. That's probably not, probably don't want to use the formula for that one again. All right, and then for number 27, we've got some kind of a survey here that we're asking people, and sometimes people responded and sometimes they refused. And this is split up by their age group. So these young people over here, 18 to 21 years old, they had 84 people that were interviewed here, and 11 said they didn't want to answer the question. All right, so we've got this table that corresponds to all the different age groups. So number 27 says, what's the probability that the selected person refused to answer? All right, so the people that refuse to answer are these 11 and 20 and 33 and 16 and so on. If you add all those up, you're going to end up that there's 156 people that refused, and there were 1,205 people altogether. So the probability that a person is going to refuse is going to be 156 out of 1,205, which ends up being about 12.9%. Okay, so 12.9% is the first part. Does the probability value suggest that refusals are a problem for pollsters? Right, well, if you have got about 13% of the people who are just going to refuse to respond, that's not a big proportion of the population, but the problem is that those people that refuse to respond are probably different from the ones that actually do respond, and I think because of that, you're going to get results that are a little bit skewed. Okay, so I think that is a problem. with people refusing to answer questions, it's not that so many of them are refusing. This isn't a high proportion. It's only about 13%. But those 13% that are refusing to answer are probably different than the people that are actually taking the survey. Okay, and then another question here is, what's the probability that the selected person responded or is in the 18 to 21 bracket? All right, so this one, I think you might want to go back and use the formula. Okay, otherwise you're going to end up having to add up a whole bunch of different probabilities. So we're saying probability that they are that they responded is going to be all of these people. So that'd be 1,049 out of 1,205. Okay, plus there were 84 out of 1,205 that were in that young age group. All right, so now if I add these two probabilities together, I'm going to get a number, and that number is going to represent the sum of these two probabilities. But there is a problem with this because there are some people that are in both groups. These 73 people are in the responders. These 73 people are also in that young age group. So we're going to have to subtract out 73 out of 1,205. All right, and when we do that, we essentially get 73 plus 255 and this and this and this and this plus this. Okay, and we don't want to count the 73 again, so we end up taking that out. So the answer to this question then is this is going to add up to 1,060 out of 1,205, which ends up being about 88%. Okay, so about 88% is the answer to that question. Okay. All right, let's move on to a few more questions here. I also want to talk about this multiplication rule. The multiplication rule is this one. Okay, it's the general rule. It's the probability of A and B. It's the probability that A occurs times the probability that B occurs given that A has already happened. All right, so if we take a look at some of these problems, let's take a look at number 7. All right, one of the big things is that we want to know whether or not these two events are independent. And if they are independent, they end up being a little bit easier to work with. All right, so we say when a baby is born, it's a girl. All right, so event A is a baby's born and it's a girl. B is when a single die is rolled, the outcome is a 6. Okay, so if we look at these two events together, does the outcome of the dice depend upon the gender of the baby? I think the answer to that is obviously not. And does the gender of the baby depend upon the outcome of the roll? Absolutely not. Okay, so if we wanted to know what's this probability, we could just take the probability that we're going to get a girl on the next baby that's born and just multiply it by the probability of getting a 6, and that's going to give me 1/2 multiplied by 1/6, and that's going to end up just giving me 1 out of 12. Okay, 1 out of 12, which is about a little bit more than 8%. Okay, so if these two things are independent, then we just multiply the probabilities together. All right, now if you look at number 9, when one of the 222 coins listed in the dataset 21 is randomly selected, it is one of the 5 Indian pennies. Okay, so they've got a collection of 222 coins, and 5 of them are these Indian pennies, which are old pennies. All right, and then B is when another one of the 222 coins listed in this data set is randomly selected, it's also one of the 5 Indian pennies. All right, so I'm assuming that we're not putting that first penny back in. All right, so if we want to know what this probability is, does the probability of B change knowing that A has already occurred? All right, well, if we've taken one of the Indian pennies out of there, that probability that the second one is going to occur is going to change. All right, so if we want to calculate that probability, we're going to say the probability that both those coins are Indian coins, so it's going to be the probability of A and B, we said is equal to the probability of A multiplied by the probability of B given that A has already occurred. So the probability that A occurs is 5 out of 222. Now we've got one of those Indian coins, there's 4 of them left, and we've got 221 left. All right, and when we multiply those two things together, we're going to end up getting about 0.000507. Okay, so a very, very small probability that we're going to end up getting 2 Indian pennies out of this 222 coins. Okay, and that should kind of make sense. It's going to be very rare that we're going to get 1, let alone 2 in a row. Okay, so those 2 events are not independent. Okay, now if we go back over or move on to question number 13, this is about pre-enrollment or pre-employment drug screening. And so this is the data up here above. It's the same data that we had on the previous page. We're going to select 2 of the 1,000 test subjects are going to be randomly selected to find the probability that they both had false positive results. Is it unlikely to randomly select 2 subjects and get 2 results that are both false positives? Okay, so if we think about these 2 events, they are not independent. Okay, the probability that we're going to get the first person is a false positive. Okay, there's 90, and there were 1,000 people altogether, so the probability the first person is a false positive is 90 out of 1,000. Okay, the probability that the next person is also a false positive, well, we've already taken one of them out, so we're going to end up with 89 out of 999. All right, and if we multiply those 2 things together, we're going to find that that probability is about 0.0081. Okay, so about 1%, a little bit less than 1%. All right, now, the problem with this is, if we wanted to know, let's say we selected, I don't know, about 5 different people, and we wanted to know what's the probability that all 5 of them are false positives. So we'd have the first person would be 90 out of 1,000. The second person would be 89 out of 999. The next person would be 88 out of 998. The next one would be 87 out of 997. And then the probability that the next one would be 86 out of 996. All right, and if you multiply all these things together, that's kind of a pain to do, but if you think about this number is exactly 0.9, and 89 out of 999 is all right, that's 0.0891. Okay, and then 88 out of 998 is 0.08817. All right, and if you look at what happens, these numbers here that I get are still pretty close to 90%. And so it'd be a whole lot easier if I could just take 0.9, multiply it by itself 5 times, and come up with an answer. All right, 0.9 raised to the 5th power is about 59%. Okay, if you multiply all these things together, you're going to end up with something that is pretty close to about 59%. It's going to be a little bit different than that, but not much. These numbers are all pretty close to 90%. All right, so what we'd like to do is we'd like to be able to do this amount of work here and assume that they are kind of independent. Okay, and really, selecting false positive results from this population really is kind of independent. Okay, we're only taking 5 people from, well, in this case, I guess we're only selecting 2 people. And so if I wanted to find out what's that probability is going to be this number right here. But if we take 90%, 90 out of 1,000, and we say, suppose that probability doesn't change, and we got 90 out of 1,000 again, we're going to end up with this answer is 0.9 times 0.9 is still 0.0081. And these answers are really close together. All right, so we're going to be able to do this sometimes, and sometimes we're not going to be able to do this. Okay, your book has a rule of thumb that says we can avoid some kind of messy calculations if our sample size is less than 5% of the population. Okay, if the sample is less than 5% of the population, we're going to assume that they are, I'm going to say, practically independent. Right? And if we say practically independent, that means that we're going to be able to do some simpler calculations and not have to worry about this, this dependency. Okay, so look for that. If you've got a sample that is just a small part of the population, that probability from one to the next isn't going to change by enough to make much difference. Okay? All right. Now, I want to take a look also at number 17 in the same assignment. Number 17 is, this is really kind of making decisions using statistics, and that's one of the things that we want to get to by the end of this course, is to be able to collect some data and make some decisions based upon the data. So number 17 says, with one method of procedure that's called acceptance sampling, a sample of items is randomly selected without replacement, and the entire batch is accepted if every item in the sample is okay. Alright, so we're going to take a sample from a big population. We're going to take 5 of them. If all 5 of them are okay, we're going to accept the batch. Okay, does that necessarily mean that everything that is in that batch is good? No, it doesn't mean that at all. It just means that this is our rule for accepting or declining a batch. Okay, so among the 8,834 cases of heart pacer malfunctions, 504 were found to be caused by firmware, which is the software programmed into the device. Okay, so 504 out of the 8,834 are because of this problem with the software. Okay, if the firmware is tested in 3 different pacemakers randomly selected from this batch of 8,834, what's the probability that the firmware in the entire batch will be accepted? Does this procedure suggest that the entire batch consists of good pacemakers? Why or why not? Okay, so we want to know what's the probability that we're going to get 3 in a row that are good. Okay, so we're going to have, first of all, 8,834 cases. We're going to select one of those. The probability that it is good, well, there's 504 of them that are bad. So if we take 8834 and subtract 504, we're going to find that 8,330 are good. Okay, so this is the probability the first one is going to be a good one. The probability that the second one is a good one. All right, now I'm going to use the, these are kind of dependent upon each other, so now we've got 8,833 left, and we've got 8,329 good ones. Okay, and then for the third one, we're going to have 8,832, and of those, we're going to have 8,328 are still good. All right, and if we multiply those 3 things together, we're going to find that that probability is about 0.838. Okay, so let's go back and think about what does this measure. Okay, this is the probability that we're going to get 3 good ones from this batch. Okay, this batch has 504 bad ones out of 8,834. All right, so that probability, 84% or so, is a fairly high probability. Okay, so what is the probability? That probability is about 84%. Now we need to be able to interpret it. Does this procedure suggest that the entire batch consists of good pacemakers? Okay, all right, now the answer is no, it doesn't. okay, the probability that we're going to end up getting 3 good ones is pretty high. Okay, so this gives me evidence to suggest that this batch is good, but we've got a high proportion of these that are really bad. Okay, so this isn't a very good procedure for determining if this is a good case. Okay, I don't think that if I had 504 bad pacemakers out of almost 9,000, I would say that that's a pretty high proportion that are bad. This technique is going to say they're good about 83% of the time. Right? That's not a very good probability, or a very good way of testing to see if the batch is bad. Okay, another problem I want to look at is number 21. All right, so for the following, ignore leap years and assume that the births on the 365 different days are all equally likely. Okay, what is the probability that a randomly selected person was born on the 4th of July? All right, well, if you just pick a random date during the year, you're going to end up with 1 out of 365. That's the probability that a person's born on the 4th of July. Okay, question number 2 says, what's the probability that 2 randomly selected people were both born on the 4th of July? Okay, so are these people independent of each other? I would say yeah. If one person's born on the 4th of July, that doesn't necessarily change the probability the next one is. So the probability that 2 people are born on the 4th of July is going to be 1 out of 365 times 1 out of 365. This probability ends up being something like 0.000. Looks like there's 5 zeros in front of this, and then 751. Okay, that's a very, very unlikely thing to happen. If I pick 2 people, that are walking through campus today and said, were you born on the 4th of July? The probability that both of them are going to say yes is going to be a very, very small probability. Okay, that's assuming that they're not twins or something else like that, something strange. Okay, this is just the probability they're both born on the 4th of July, really, really small probability. Okay, then part C says, what's the probability that 2 randomly selected people were born on the same day? All right, so if we think about that in terms of 2 events, the probability, if we look at each person individually, it really doesn't make any difference what day this guy was born. He's got a 365 out of 365. He could be born on any day we want. But then, what's the probability that the second person's birthday is going to match his? Well, he was born on one day out of those 365. So the probability is going to be basically 1 times 1 out of 365. And the probability that 2 people were born on the same day is going to be like 0.00274. All right, so a much higher probability than born on the 4th of July. Okay, and actually this answer ends up being 365 times this answer. Okay, so again, in independent events we can multiply the probabilities together. If they're not independent, then we can't multiply them together. Okay, the next one I want to look at is 23. Screening for marijuana use. If 2 subjects are randomly selected without replacement, what's the probability they both had correct results? All right, so this one we're given some information here, and they suggest that we set up a table with false positives and false negatives and so on. So we are going to have people that use and that don't use. We're going to have tests that are positive and tests that are negative. Okay, so this is the use and this is the test. Alright, so if people are using, let's see, what does it say? Among the 143 subjects with positive test results, alright, so there was 143 of these people. There were 24 false positives. Okay, so a false positive is they test positive but they don't really use. So there's 24 here, and then the rest of them, 143 minus 24, that's going to give me 119. Okay, 119 are users and test positive. Okay, and then it also says among the 157 negative results, so there was 157 of these people, there are 3 false negatives. Alright, so these people are the ones that are testing negative, but they used drugs. There was 3 of them in this category, which means there was 154 left over. Okay, so if we look at what number of drug users there are, there's going to be 122, and here there's going to be 178, which gives me a grand total of what? 300. Okay, so there's 300 people altogether. So now I think that we can answer the question a little bit easier. All right, so screening for marijuana use. The question says, if 2 of the subjects are randomly selected without replacement, what's the probability that they both had correct test results, either true positive or true negative? All right, so where are those people? Okay, those people are going to be the ones that use drugs and the test positive, and they're also going to be these people down here that don't use drugs and test negative. All right, so the probability of being in this first group is 119 out of 300. Probability of being in this group is 154 out of 300. Okay, and the question says, you subtract, take 2 people are selected without replacement. What is the probability that they both had correct test results? Okay, so there were, what, 119 plus 154 is, what, 2, 6, 3, 2, 73. Okay, there's 273 people that are in one of those 2 groups. Now, we're going to take one person first, and we're going to end up with 273 out of 300 is the probability the first person I select is one of these that gets a positive test that uses or a negative test that doesn't use. Then once I've selected one of those people, now I've only got 272 of them left out of 299. All right, and if I multiply those 2 probabilities together, we're going to end up with about 0.828. Okay. All right. Now the question is this event unlikely? All right. Well, if something happens about 83% of the time, I would say that's not unlikely. All right. So about 83% of the time, our test comes up with the results that it should come up with. Okay, which makes me think that that's not a bad test. Okay. Next one, number 27. This one says, find the probabilities and indicate when the 5% guideline for cumbersome calculations is used. All right, so here, in the Prince Market Research survey of 2,518 motorists, 252 said that they made an obscene gesture in the previous month. Okay, if one of the surveyed motorists is randomly selected, what's the probability that this motorist did not make an obscene gesture? All right, so this is going to be the complement rule. All right, we're going to end up with, we've got 2,518 people in this group. 252 said that they did make an obscene gesture. So the number that are left then would be 2,518 minus 252. That gives me 2,266. All right, and if you divide those, you're going to come up with an answer that's about 90%. Okay, next one. If 50 of the surveyed motorists are randomly selected without replacement, what's the probability that none of them made an obscene gesture? All right, so if we look at this, here's what we're going to have to do. We're going to have to say 2,266 out of 2,518 would be the probability that the first person I asked did not flip somebody off. The next question, or the next person, is going to be, there's going to be 2,265 of them left, and there's going to be 2,517 left in the pool. Right, then we're going to end up with 2,264 out of 2,516, and we're going to have to do this like 50 times. Okay, that sounds to me like what your book calls a cumbersome calculation. All right, what I'd like to be able to do is say, you know what, we're only going to take 50, and we're taking 50 out of the 2,518. And 50 divided by 2,518 gives me about 1.9%. All right, so here's what we're going to say. These probabilities don't change by very much. All right, and they're all going to be just about 90%. It's going to be a whole lot easier for me to take 0.9 50 times, or just take 0.9 and raise to the 50th power. And if I take 0.9 and raise to the 50th power, I'm going to get an answer that's pretty close to the right answer, which is going to be about 0.00513. Okay? All right, so not very likely that we're going to end up with everybody in my sample was kind to their fellow motorists. Okay? Very unlikely that we're going to get 50 people in a row that did not flip somebody off. Okay. Let's take a look at just a little bit more. The next section is about the multiplication rule. All right, I do want to go through a few of these problems as well. All right, number 8 says when 4 digits between 0 and 9 inclusive are randomly selected with replacement for the lottery ticket, what's the probability that none of the digits is a 7? Okay, so if you think about what's the probability the first digit's not a 7, that's going to be 90%. Probability the next one's not a 7, 90% again. Remember, we're doing this with replacement. And then 3 in a row is going to be times 90% again and times 90% again. All right, and if I multiply all this together, we're going to end up with about 0.344. So about 34.4% is the probability we're going to get no 7s. Okay? And if you take a look at number 9, if you make random guesses for 10 multiple choice test questions, each with 5 possible answers, what's the probability of getting at least one correct? Okay, if we're very lenient, or if a very lenient instructor says that passing the test occurs if there is at least one correct answer, can you reasonably expect to pass by guessing? All right, so if you think about the probability of getting at least one right, now, if you really think about that, there's a whole bunch of different ways that you could get at least one right. Okay? This is really a case for, you really need to look at that at least one phrase. Probability of at least one. And this is something that you really should take into account, is the probability of at least one is the complement of none. Probability of at least one is 1 minus the probability of none. All right, it's going to be a lot more. It's going to be a lot easier for me to figure out what's the probability that a person got none of them right. Okay, so in order to get none of them right, you're going to have to miss the first one. The probability you're going to miss the first one is you've got choices A through E, so there's going to be about a 20% chance that you're going to get the first one right, which means there's an 80% chance that you're going to get the first one wrong. Okay, and then the next one is going to be 80% again, and then 80% again, and we're going to end up with 10 of these. Right, and these are all independent. Okay, getting the first one right doesn't change the probability of getting the next one right. So all of this is going to be the probability of getting none of them right. And then if I take 1 minus that, that's going to give me the answer that I'm looking for. Okay, and that answer ends up being about 89.3%. Okay, so if you've got a professor that says he's going to let you pass if you can get at least one correct, can you reasonably expect to pass by guessing? Okay, this is the probability you're going to pass. That's a pretty high probability. That's about 90%. 90% chance you're going to pass this test. I would say that that's a pretty high probability. All right. Next one is number 16. 16 says is about cleared burglaries. According to the FBI, about 12.4% of all burglaries are cleared with arrest. In other words, they've caught the person that did it. A new detective is assigned to 5 different burglaries. What's the probability at least one of them is cleared? All right, so again, here's that phrase, at least one. we should be thinking about 1 minus the probability of none. All right, so we got 5 cases here. The probability that any of those is going to be cleared is going to be 12.4%. The probability that they're not going to be cleared is going to be the complement of that, which is 0.876. All right, and so we're going to end up taking 0.876 and multiplying it by, we've got new detective has 5 cases. There's going to be 5 of these that are not going to be cleared. 1 minus that is going to give me the answer I'm looking for, which is about 48.4%. Okay, so that's the answer to part A. What's the probability that the detective clears all 5 burglaries? Okay, well that's going to be 0.124 times itself 5 times. And we're going to come up with an answer here that is 0.000293. Right, so not a very good chance that that all 5 of them are going to be cleared, but there is a pretty good chance that we're going to get at least one of them cleared. What should we conclude if the detective clears all 5 burglaries? All right, so the likelihood of him clearing all 5 burglaries just kind of by chance is going to be very, very small. All right, so one of 2 things happens here. One is maybe this guy is just really, really good, okay, that he knows how to clear these burglaries. The other thing is that maybe these were really 5 cases that were pretty easy to solve. All right, so that probability is actually going to change from one to the next. But the idea here is that that probability is really, really small, and that's the way we should interpret it, is that he's probably a really, really good detective. Okay. The next thing I'd like to look at is going back to your formula sheet. Okay, we kind of skipped over this part. All right, but what does it mean for these 2 events to be independent? Okay, this says the probability of A given B. All right, well, if these 2 events are independent, the probability of A given B should just be equal to the probability of A, whether we know the result of B or not. And the probability of B given A, that should just be equal to the probability of B. All right, and then if they are independent, the probability of both is going to be equal to just the probability of A times the probability of B given A, which is just the probability of B. Okay, so this formula here and this formula here are really the same formula. The only difference is if they are independent, this probability of B is the same thing as this. Okay? All right, now we've got the conditional probabilities. I think we've got everything on that list that we need. All right, so now I'd like to take a look at these problems. All right, and I'm going to tell you that these problems are not, they're not just trivial questions. Okay, so let's look at question number 1. You got a large statistics class. 20% of the class earned an A on the first exam. 25 earned an A on the second exam, and 16 earned an A on both exams. If a student is drawn at random from this class, what's the probability of each of the following? Okay, the person earned an A on at least one of the exams. All right, now I'm going to tell you that we probably should go down to here and see if these are independent, all right, because that's really going to help me to answer the question up above. First of all, F is the probability of the person, or the event that a person got an A on the first exam. S is the A on the second. Are they disjoint? And the answer to that one, I hope, is painfully obvious that they are not disjoint, because there were 16% that got A's on both exams. Okay, the probability of F and S is not 0. Okay, it's equal to 16%. Okay, now are they independent? That's a little bit different, because now we have to look at what's the probability of getting an A on the first exam. Is that the same thing as the probability of getting an A on the first exam, given that they also got an A on the second exam? Okay, now this question, I think that we should probably be careful with this, because if a person got an A on the first exam, they're probably more likely to have gotten an A on the second exam. Okay, the smart kids probably got A's on both exams. All right, so what I'd like to look at up here is a way of organizing the information that's given here, right? And there's two ways that we could do that. One way is we could set up a table. Right, we could say up here is the first exam, over here is the second exam. Right, and it says that 20% of the class earned an A on the first exam. Right, now it is kind of safe to say, what if we had 100 kids? We would end up with 20 of them got an A on the first exam. Right, so this is the A's, this is the not A's. And this is the A's, and this is the not A's. 20% of the class got an A on the first exam. Okay, so there's going to be 20 kids here, right, which means that 80% of the kids did not get A's on the first exam. All right, then 25% got an A on the second exam. Right, so this is going to be 25 over here, which means that 75 are here. Right, then it also says that 16% got an A on both exams. So let's put 16 here, which means that on the first exam, if 16 of them got A's, that means that the rest of them, 9, did not get A's. Okay? And then if there are 16 of these here, and there's 20 here, that means that 4 of them had to not get A's here. And then if you look at this is 80, and this is 75 this way, this has got to be, what, 71 kids in this group. Okay? All right, and then if we think about this is 100%. Okay, so now, what's the probability the person earned an A on at least one of the exams? Okay, so the question is, did these kids earn an A on at least one exam? And the answer to that is yes. Did these kids get an A on at least one exam? Yeah, they got an A on the second one. This one, those kids got A's on the first exam. These kids down here didn't get A's on either exam. So the probability that a person got an A on at least one is going to be what I get when I add those up, and we're going to end up with 29%. Okay, what about a person earned an A on exactly one of the exams? Okay, so it's not these kids. They got A's on both. These kids didn't get A's, so it's got to be just these two. Okay, that's 13 out of 100 is just 13%. Okay, then the person earned an A on the second test given that he earned an A on the first. All right, so this one is a little bit tricky. So we're saying given that they earned an A on the first exam. Okay, so we're talking about these 20 kids. And if we talk about just those 20 kids, of those 20 who got A's on the first exam also, that's going to be 16 out of 20. 16 out of 20 of the kids that got A's on the first exam also got A's on the second exam. Okay, now another way you could look at this is the probability of first and second, and then divided by the probability of first. The probability of getting A's on both exams, 16 out of 100. The probability of getting an A on the first exam is 20 out of 100, which is going to reduce to 16 out of 20, which is 80%. Okay, a person did not earn an A on either exam. That's going to be these 71 kids down here, so 71% of those kids. Okay, so how about this? Is the probability of getting an A on the first exam equal to the probability of getting an A on the first exam, given that they got an A on the second? So the left side of this equation, probability of getting an A on the first exam, that's 20%. There were 20 kids out of 100 that got A's on the first exam. All right, then I want to know, is that equal to the probability of getting an A on the first, given that they got an A on the second? Okay, there was 25 kids got an A on the second. Of those 25 kids, 16 of them got A's on the first exam. 16 out of 25 ends up being 64%. 20% is not 64%. Okay, so these are not independent. Okay, these probabilities are not the same thing. All right, so I'm going to tell you that conditional probability like this is a little bit different to think about, and there's a lot of places to make mistakes, and I think being able to organize some information in a table like this a lot of times is very beneficial. Okay, so there's another kind of way to organize thoughts with probabilities, and that is this problem tells you a lot of information about people who drink coffee, tea, and cola. All right, and what I want to know is what percent drink cola only and what percent drink none of the beverages. All right, so I'm going to think about this in terms of, it's called a Venn diagram. All right, and this Venn diagram is going to represent people who drink coffee, people who drink cola, and people who drink tea. Okay, and so we're given a bunch of information. So 55% of the adults drink coffee. Right now, that 55% is going to have to be split up into 4 different kinds of people. Okay, those 4 kinds of people. These kinds of people out here drink coffee only, no cola and no tea. People that are in here drink all 3 of the sources. The people that are here drink coffee and tea, but not both. And then the people here drink cola and coffee. People here drink coffee and tea, but not cola. And the people that are here drink cola and coffee, but not tea. All right, so we're getting a bunch of different places here, and I think what I would start with is that 5% drink all 3. All right, so I'm going to fill this little cell in here as 5%, or it might be easier to think about this in terms of out of 100 people. Out of 100 people, 5 of them drink all 3 of them. All right, then if I look at the other things that are here, 15% drink both coffee and tea. So coffee and tea is everything that's in this kind of football shape. Okay, 15% is in there. We've already accounted for 5%, which means that this has to be 10%. Drink coffee and tea, but not cola. Then the next one, 25% drink both coffee and cola. So we're talking about the people that are in this group. Okay, we've already accounted for 5 of them. The other 20 are going to have to be here. And then 5% drink tea only. That means that there's going to be 5 out here. All right, then I think we can go back up here and start using some of this information. 55% of all adults drink coffee. Okay, we've already accounted for, what, 35% of them, which means that there's got to be another 20% out here. 25% drink tea. We've already accounted for 20, which means there's got to be 5 more here. And then 45% drink cola, and we've accounted for 30% so far, so there's got to be another 15% out here. Okay, so now, once we get that set up, I think that part A should be trivial. What percent of adults drink cola only? Right, so we're talking about just those. That's 15%. And then what percent drink none of the beverages? Right, well, we haven't really talked about where none is, but none is going to be everything that's on the outside of all these circles. And if you add up everything that's on the inside, these are all the people that drink at least one of these. So we're going to have 20, and 20 is 40, and 15 is 55, 65, 70, 75, 80, which means there's got to be 20 people left over out here, which means that 20% of the population don't drink any of these beverages. Okay, again, these problems I don't think are really trivial, but I think that once you set this up in a Venn diagram, it ends up being a lot easier to think about instead of just looking at all of these different statements and trying to put all those together and keep track of all these people. All right, the next one. Okay, this one says, at a very large school district. Okay, so we're saying that there's a whole bunch of kids in this district, and 30% of them take calculus. Of those taking calculus, 80% also take physics. Okay, so this 80% is a conditional probability. It's the probability of taking physics given that they take calculus. Also, 66.5% of all students take neither course. If a student is drawn at random from the school, what's the probability of each of the following? Right? This says make a tree diagram. Your book doesn't talk much about tree diagrams, but I think that they are very beneficial. All right, so we're going to look at these people that are in the school or in this school district, and we're going to say some of these people take calculus, some of them don't take calculus. So this is calculus, and this is no calculus. Okay, the probability that a person is going to be selected that takes calculus is going to be 30%. The probability that they don't is going to be 70%. All right, and then once we determine if they take calculus or not, then we've got physics or no physics. Okay, so the probability here is the probability that a student takes physics, and we already know that they take calculus. That branch is going to be 80%. Okay, and then the probability that they don't is going to be the complement of that, which is 20%. So if we look at multiplying along these branches, 30% times 80% is going to give me 24%. That 24% represents the kids that take both classes. Okay, if I multiply across here, we're going to get 20% times 30%, that's 0.06. 6% of the students take calculus, but they don't take physics. All right, and then the other 66.5% is really the kids don't take calculus and they don't take physics. All right, so this is 0.665. All right, so whatever number goes here is going to be 70% times this is going to give me 66.5%. This probability ends up being 90%. Okay, 70% times 90, is that, no, it's 95%. Okay, 70% times 95% is going to give me 66.5, which means that this has got to be 0.05. All right, then if I multiply across this way, we're going to get 0.035. Okay, so with this tree diagram, I think we should be able to answer a lot of these questions fairly easily. These are the kids that take both classes. These kids take calculus but no physics. These kids take physics but no calculus. And these kids don't take any. Okay, so what's the probability a student takes physics but not calculus? That's these guys right here. 3.5%. Student takes calculus but no physics. They take calculus but no physics. That's going to give me 0.06. The student takes at least one of the courses. Okay, here's that at least one again. So there's two ways you could do this. You could say these kids take at least one, these kids take at least one, and these kids take at least one, and add them together. All right, if you take those three and add them together, you're going to get 0.24 plus 0.06 plus 0.035, and that's going to give you 0.335. An easier way to do that is takes at least one course is the complement of none. That's going to be 1 minus 0.665. That answer is also 33.5%. It doesn't really make any difference which way you do that, but in this case, but in a lot of cases, using that complement rule is going to really help out. Okay, student takes at least one of the two courses. Sorry, takes exactly one of the two courses. Okay, that's going to be these kids here and these kids here. Okay, these kids take calculus but no physics. These kids take physics and no calculus. That's going to be what I get when I add those together is 0.9 or 0.095. Student takes calculus given that he takes physics. Okay, so this is probability that the student takes calculus given that he takes physics. All right, now this one I think might be easier if I use my formula. Okay, this isn't the 80%. That 80% is the probability they take physics given that they take calculus. This is going to be the probability if they take calculus and physics. And then remember our formula says divide that by the probability of the given part. Okay, so the probability that students take both, 80%. Okay, that's this number, or no, I'm sorry, 24%. The probability that a student takes physics, well, probability a student takes physics, there's going to be 24% take physics with calculus, and there's going to be another 3.5% that take physics without calculus. So we're going to divide that by 0.24, plus 0.035. Okay, then whatever you get for an answer there is going to be slightly less than it's going to be slightly less than 1. Okay, 5 students are chosen at random. What's the probability that none of them take calculus? All right, now we're going to have to make an assumption here that this is a really, really large school district, and we're selecting 5 of them. 5 students is going to be less than 5% of that population. So we're going to assume that the probability of a student taking calculus is going to stay constant. So 5 students at random, what's the probability none of them take calculus? All right, well, 30% do, which means that 70% don't. So we're going to take 70% times 70% times 70% 5 times, and then whatever we get for an answer there, 0.7 to the 5th power. Okay, that's not going to be the exact answer, but it's going to give us a lot easier way than doing all those conditional probabilities. And because 5 is a very small proportion of this entire population, we're going to get that my answer can be approximated by this number pretty accurately. Okay, 5 students are chosen at random. What's the probability that at least 1 takes calculus? Okay, this is one where I think we want to do the complement rule. This is going to be 1 minus the probability of none. So probability that none of the 5 take calculus, that's going to be 1 minus. Okay, the first person doesn't take calculus, that's going to be 0.7. The next one doesn't take calculus, it's going to be another 0.7. We're going to end up with 5 of those. Right, so whatever we get for an answer here, these 2 answers are going to end up just being complements of each other. Okay? All right, so again, those problems are a little bit more challenging, but I think that if you can get those problems and understand those, that the rest of the problems should be, I think, quite a bit easier. I think that the problems that were in the textbook were much easier than some of the problems that I've done in class, and much more easy than the ones that were definitely on that handout. All right, so that should take us up through section 4.5. You do still have your test on Thursday. I'm going to take part of the beginning of that time to do a little bit of review and answer questions, and then the test is going to will take about 45 minutes to an hour for everybody to get done, so we'll do that the second half of the exam. I'm going to tell you also that I gave you the first 2 quizzes that were that take-home that were all about experimental design and sampling, and then the second one was about measures of center, measures of spread, standard deviations, means, and things like that. Those are going to show up on this exam, but I'm going to also tell you that the stuff about probability is going to be weighted heavily, and then also the stuff on linear regression and correlation is going to be another thing that is going to be the majority of the test. All right, so I would say that between Chapter 4 and Chapter 10, that's going to make up probably about 3/4 of the exam, 2/3 to 3/4 of the exam. The rest of it is going to come from those first 2 chapters. Okay, and again, you should probably be able to read that in the email that I'm sending out. Okay, so that's all I've got for tonight, and I will see you all on Thursday. And again, we'll take questions at the beginning, and then your exam is going to be on Thursday. So thanks for watching this video. I hope that you got everything out of it that you needed to get out of it. All right, thanks. Have a good night, and I'll see you on Thursday.